All right, good morning, good afternoon, good evening to everyone that's watching at whatever time that you're watching. Today, we're going to be talking about Dalton's law of partial pressure. So, this is kind of not really a big part of chemistry, but it kind of does play a big role in general chemistry, especially in college. So, you're going to want to have a good understanding of partial pressure. So, what is partial pressure? What is that law? So, if we're going to talk about the textbook definition, this is what it is. You can skip this part if you want. I will simplify it after I read this. But this says if molecules do not attract or repel one another, then the pressure exerted by one type of molecule is unaffected by the presence of another gas. Consequently, the total pressure is given by the sum of individual gas pressures. So, how I would explain this in the most simple terms is that all of your pressures, when they're added up, are going to equal the total pressure, right? So if you have, let's say, P1 plus P2 plus P3, you have 3 different pressures. Those are all going to be added up to make your total pressure. So that would be the simplest way that I would explain it, is that all of your pressures are going to add up to have your total pressure. So what exactly does this mean? This is a pretty important formula when it comes to solving partial pressure problems. So pretty much how I look at this formula, if I were to label each of these, different variables in the problem, I would immediately go here. We kind of already introduced it down here. This is your total pressure. This is normally going to be given to you in the problem, but it'll be in torr, it'll be in kilopascals. So we can just write that down. It could be in atmospheres. So for this, you're definitely going to want to know your labels so you know that this is actually going to be your total pressure. Now, this one, I kind of look at that as like the substance that you're trying to find the partial pressure of. So I'm going to put substance or element. Normally a problem will say find the partial pressure of O2 or nitrogen gas or something like that. And that would be this substance right here. This is normally the variable that you're going to be solving for. Now, what's this one? The XI. That one actually is its own thing. You're going to have to kind of memorize that. This is the mole ratio. And pretty much, if we were to break this down, it would be the moles of your substance that you're trying to find, so of the element in question, over the total number of moles. Oops. So obviously, this isn't really going to do much for you if we don't have a practice problem, but this is the basic setup. This is the formula that you're always going to want. You're always going to need a total pressure. You're always going to have the substance that you're solving for, and you're always going to have your moles of the element over the total moles. Now, obviously, because we know all these, if they give us maybe the partial pressure of a substance or element, maybe we'll have to solve for this. But they will, in a problem, normally give us all the information we need in order to solve for one of the variables. So we'll start off with a super basic problem. This video is going to be basic partial pressure problems. I am going to try to do another video with some extra partial pressure practice, but I will write this formula on on our papers as we go. So let's just start with this problem. Can we see it? There we go. So calculate the partial pressure of each of the following gases. So there's lots of numbers, lots of letters, lots of information going on. But I think the first thing that we can try to do is focus on one at a time. So again, our partial pressure formula is substance equals our mole ratio, which honestly, I'll just write it as our mole ratio. So moles of substance or element over total mole times our total pressure. So I think the first thing that we can try to do is, one, we'll just ignore, I'm just going to do this and see if this helps. We're going to ignore the other two, and we're going to just find the partial pressure of CH4. So what is the partial pressure of CH4? So I'll kind of walk us through the first one step by step. So what is our substance? Our substance is CH4. That's the substance that we're trying to find. This part of the equation is our substance. So let's start with number 1, CH4. So we're going to write the partial pressure of CH4. So this I gets replaced with our substance equals. Now, how many moles do we have of our substance? It tells us right in the problem. We have 0.31 moles over. Now, I guess we can't really ignore the other ones because we need the total. So the total, let's write this out. Our total mole value would be 0.31 plus 0.25 plus 0.29, right? So we'll plug that in. 0.31 plus 0.25 plus 0.29 gets us 0.85 total moles. So then we have our moles of our CH4. If it helps to put CH4 over here to remind you that that's what we're solving for, I will just do that for the sake of this problem. Over our total, which is 0.85 times our total pressure, which is given to us in the problem right here, which is 1.5 atmospheres. So then all we do is we literally just plug in the numbers and solve. So I normally go 0.31. I solve this first. So 0.31 divided by 0.85. And then don't round off. Just times it by 1.50 right away. And we get a partial pressure of 0.547. Let's just say that. For number 1. So that would be your answer. Now, partial pressure, since the total pressure is in ATM, your unit for this one would also be an ATM. Because here, I should write the units. Moles would both cancel, and you'd be left with ATM as your final unit, which is why you'd have ATM here. Okay, so let's do number 2, and we'll go a little bit quicker. I'm running out of room on this paper. Okay, so we have our substance for number 2, which is C2H6. So the partial pressure of C2H6 equals our number of moles for that substance, which is 0.25 over our total, which we calculated to be 0.85 moles, times our total pressure, which again was given to us as 1.5 ATM. We can calculate this out and do 0.25 divided by 0.85 times it by the 1.5, and we're left with 0.442 ATM. Now, in terms of sig figs, that's something that you'll have to discuss with your professor or your instructor on how they want to do their sig figs, because each teacher is different. And then number 3, we're on C3H8. So our substance is C3H8. Oh, shoot, can't even see it. equals our number of moles, which is 0.29, over our total, which was 0.85. We calculated that, times by the total pressure, which is given to us as 1.5 atm. Plug those numbers in. 0.29 divided by 8.85 times 1.5. So 0.512 atm. Now, let's say, are these partial pressures right? You don't know if they're right. Maybe you don't know if you did the problem correctly. So we can do a check. Let's just do it right here because there's room. And we know our total pressure is 1.5. So all of these pressures should equal 1.5 because remember, Dalton's law of partial pressure is that all of our individual pressures should add up to the total pressure. So we can go ahead and just see if these add up. So we'll take 0.547 plus 0.442 plus 0.512, and we get 1.501, but literally it checks out to 1.5. So we know we did our math right, and we know we did our problem correctly. Okay, so that one, not so bad. A lot of numbers. It's a lot of keeping numbers straight. So let's do another problem. This is kind of a word problem where you're going to have to pick out the important information. So what is the partial pressure of CO2 in a container that holds 5 moles of CO2, 3 moles of N2, and 1 mole of H2, and has a total pressure of 1.5? So that's a lot of information in this problem. So let's kind of pick and choose what information is useful and where it would go in our formula. So just to remind us of our formula, we have our partial pressure of our substance equals our moles of the substance over total moles times total pressure. That's our formula. So maybe what we should do is we should ask, what are they asking? What are we trying to find? What information do we have? And where does it go in our formula? So do we know what we're trying to find? Well, what does the question say? We know we have to find a partial pressure of something, right? So we look back in the question and it says, what is the partial pressure of CO2? So that's our ticket. This is the substance we're trying to find, CO2. So we can start by filling that information in to our formula. So we know we're trying to find the partial pressure of CO2. Okay. Do we know this information? The moles of the substance over the total moles. So then we continue reading. In a container that holds 5 moles of CO2, 3 moles of N2, and 1 mole of H2. So what do we do with this information? It tells us the exact number of moles of CO2 that we have, and that's the substance we're trying to find. So we know that we can plug in our moles of our substance. That would be 5 moles. Because it gives it to us right in the problem. Let me underline it so that we know that it's important. So that goes right in here. So do we know our total moles? That would be our next question. It doesn't explicitly tell us our total moles, but we can for sure calculate it because it gives us all of the moles that are within this container. So how would we get our total moles? We have 5 moles, 3 moles, and 1 mole. How would we get our total moles? All we have to do is add them up. So let's do that right now. Let's do that right here. Total moles is 5 moles plus 3 moles of our N2 plus our 1 mole of H2. So that gets us 9 moles, right? So 5, 6, 7, 8, 9 total moles. So now where would this go? Our total moles. So we'd have 9 moles total. So we know we filled out the whole first portion of our formula. Our last portion is our total pressure. So let's keep reading our problem. So a container that holds 5 moles of CO2, 3 moles of N2, and 1 mole of H2 and has a total pressure, keyword there, total pressure of 1.05 atm. Another keyword right there would be your unit of atm. So these are 2 key points that are going to point you towards your total pressure. So our total pressure is 1.05 atm. So that would go in the total pressure slot. Then all you do is get your calculator and calculate it out. So we'll do the 5 divided by 9 and then times it by 1.05. And that gets us 0.583, and then unit atm, and that would be your partial pressure for CO2. Now, if you wanted to check this answer, you could totally find all the partial pressures of all of the other elements. So you could do this exact same process for N2 and H2 and then add them up and see if you get the total pressure. I'm not going to do that for this problem because we did it for the first problem, but ideally, if you did all of your calculations correctly, this number should be correct. Also, you know it's going to be a relatively big number because it has the most moles in the container. So it's going to take up the majority of that pressure. Now we have one more problem that we're going to do, which is this one. So water decomposes in an evacuated chamber. The final pressure is 600 torr. What is the partial pressure of O2? And then we have a equation. This is a lot. There's a lot going on here with this problem, especially when you have an equation. I always find that it just adds on another layer of stress because it's just a lot going on. The first step would definitely be figuring out that formula. So having that formula handy, I'm just going to write XI. XI stands for the moles of element over the total moles. I'm just going to write XI to keep it short and sweet, since we kind of know what this stands for now. So having this handy is important. Then figuring out, what am I trying to solve here? What am I solving for? What partial pressure am I looking for? So let's read the question. We already did, but let's read it again. Water decomposes in an evacuated chamber. The final pressure is 600 torr. What is the partial pressure of O2? So here's our question. When it has the what is, you know that's the question. So probably after that, it's going to be asking you what you're looking for. So we're trying to find the partial pressure of O2. So we can go ahead and write this down here and get our equation started. Partial pressure of O2. It may even help to write a question mark there. Sometimes I find that helps remind me that, hey, this is what we don't know. We don't know the partial pressure of this guy. So now what? we need to find our moles of our element over the total moles. Well, it doesn't give us the moles in the problem like our previous ones. So what are we going to do? It's stressful. It definitely requires some thinking here because it's a different type of problem, but that's why we're going over it so you guys can be familiar with what you may see on an exam, because when I first saw this, I had no idea where to even start. So luckily, they give us this lovely, lovely equation here. These coefficients represent, now keep in mind that in front of the O2 here, there's a 1 as a coefficient. But we don't write the 1 because it's just not necessary. But remember that there is a 1 coefficient in front of this. These coefficients represent the number of moles of that substance in this case, in the chamber. So how would we find our moles of our element? Well, we're going to look at our coefficients because, like I said, these coefficients are telling us how many moles of each substance there is. So in this chamber, we have 2 moles of liquid water, 2 moles of hydrogen gas, and 1 mole of oxygen gas. So we put in our 2 moles of liquid water into the chamber, and it decomposes into these substances. 2 moles of H2 gas, 1 mole of O2 gas. So we're trying to find the partial pressure of O2, which we have here. So what would be our number of moles of O2 in this chamber? Because that's what we're trying to find. We need our moles of our element over our total number of moles. Well, based on our equation, we know that there's 1 mole of O2 gas in this chamber after the water decomposes. So that's what would be on the top. 1 mole of O2. How many total moles are there in this chamber after the water decomposes? Well, we have 2 moles of H2, 1 mole of O2. So all we would do is take these numbers and we would go 2 plus 1 equals 3. There's 3 total moles in this chamber after the water decomposes. So we'd have 1 over 3 moles. Now, if this was confusing, please rewind the video and watch it again. It was confusing to me when I first learned it. But just remember, just imagine that this isn't even in the equation and the problem is saying there's 2 moles of H2 and 1 mole of O2, because that's all these coefficients are telling you, is how many moles of each substance are in that chamber. And then times our total pressure. Now, again, another question. It doesn't tell us explicitly what the total pressure is. It doesn't say the total pressure of the substance is blank. In this case, it uses the words final pressure is 600 torr. Normally, there's only going to be 1 pressure value. Again, considering the pressure units, and then just pretty much the same thing as final pressure. But this is saying, you know, it's another way of saying total pressure, but instead they're saying final pressure. So you would take this information and come to the conclusion that 600 torr is your total pressure. So then 600 torr would go here. Now, you might be saying, well, how do I know what unit this needs to be in? What if it needs to be in a different unit? For now, if it's given in torr and this problem doesn't specify, then it's probably going to want the unit in the same unit that it was given in the problem. So you don't need to convert this to anything. It's not like some of our other formulas where it needs to be in a specific unit in order to get the correct answer. So then we do 1 divided by 3 times by 600, which would be 200. Now, like I said, moles cancel during the dividing process, and then we're left with torr. So our unit would be torr. So just make sure that when you're doing the problems that the units aren't always going to be ATM or aren't always going to just be torr. They're going to be whatever they give you here in the problem. that unit will come down here, and that will be your ending unit. Again, this would make sense because there's only 1 mole of O2. So we know that this number is going to be smaller. Pretty much what I'm saying is that we know there's 2 moles of H2. So if this number were to come out to be like, I don't know, 500, we know that there was something wrong there, because that means that this would be way less. And that doesn't make sense because there's more moles of H2 than there are O2. So that's it for the basic problems and setup of partial pressure problems. I am going to upload another video with some more advanced partial pressure problems where you're going to have different formats. If you have any questions on how to do this, or maybe there's an error in the video, or you have a tip that you think would be a lot easier, please leave it in the comments. And hopefully this helps you guys with some general chemistry stuff. Good luck.